A field camera in Cougar captured something last dry season that changed how our team models predation events. A male leopard, roughly 70 kilograms, dropped from a marula tree onto an adult impala. From branch release to cervical dislocation, 1.4 seconds. We've reviewed that footage over 200 times. The impala's legs hadn't finished their first reflex extension before the spine was already compromised. That clip forced us to restructure our entire ranking framework. Because when you stop sorting predators by mass, which tells you almost nothing about lethality, and start sorting them by time to incapacitation, the hierarchy of wild cats reorganizes itself completely. This is the data. Before we rank anything, we define the metric. Time to incapacitation, or TTI, is the interval between first physical contact and the cessation of coordinated prey resistance. Not death, resistance. The moment the prey animal can no longer execute an escape behavior. This distinction matters because different cats achieve incapacitation through entirely different mechanical pathways. Some are strangulation specialists. Some are vertebrae crushers. Some are high-speed ambushers whose kills finish before the prey's adrenal response even peaks. Our data separates these cats into 3 operational tiers based on TTI, and what emerges is a study in target-specific lethality. Each species has evolved to attack a precise anatomical structure using a biomechanical system purpose-built for that single task. Leopards and cougars share a kill architecture we classify as the vertical ambush. Both species preferentially attack from an elevated position, tree canopy for leopards, rocky overhangs for cougars, converting gravitational potential energy directly into impact force on the prey's dorsal neck region. What makes leopards mechanically exceptional is a feature our biomechanics colleagues have termed elastic ligament recoil. The nuchal ligament system along the leopard's spine stores elastic energy during the crouch phase and releases it during the launch, functioning almost identically to a drawn bowstring. This is not standard muscular contraction. This is a passive energy return system, and it means the leopard's initial strike velocity exceeds what its muscle mass alone could produce. The cougar employs a similar vertical model, but relies more heavily on raw hind limb power. A cougar dropping from a 6-foot ledge onto a mule deer generates enough force to buckle the cervical vertebrae on contact. Both species target the nape. Both species use a rapid bite and twist that laterally displaces the C2-C3 vertebral junction. The prey's motor function collapses almost immediately. The animal is not dead, but it is incapacitated. And in this framework, that is the only number that counts. The jaguar does something no other wildcat does routinely. It bites through the skull. Our field data from the Pantanal documents jaguars killing caiman, animals armored with dermal osteoderms, by puncturing the cranial vault between the parietal bones. This is not opportunistic. This is the default kill method. The jaguar has evolved for the cranial bite. The mechanical basis is the sagittal crest leverage system. The jaguar's sagittal crest, the bony ridge running along the top of the skull, is proportionally the largest of any extant felid. A larger crest means a longer muscle fiber attachment, which means greater contractile force at the canine tips. Our measurements put the jaguar's bite force at roughly 1,500 psi at the canine. For context, a lion, an animal that can weigh twice as much, generates approximately 650 psi. The jaguar doesn't need a prolonged hold. It doesn't need strangulation. It applies a single catastrophic compression to the temporal or parietal bone and causes immediate neurological shutdown. This is the fastest reliable TTI in our dataset. When the jaguar secures a cranial bite, prey resistance drops to 0 in under a second. The brain doesn't have time to register pain before it ceases to function. This is where our ranking may surprise some viewers. The lion, the animal most associated with apex predation, has the longest TTI in our framework by a significant margin. Lions are strangulation specialists. Their standard kill method is a sustained muzzle clamp or throat bite that occludes the trachea and compresses the carotid arteries. We call this the asphyxiation clock, and it runs long. Field observations show that a solo lioness maintaining a throat hold on a wildebeest requires an average of 6 to 8 minutes to achieve full incapacitation. On larger prey, Cape buffalo, eland, that window extends past 10.
The lion's jaw musculature is built for endurance, not peak force. High oxidative slow twitch fibers dominate the masseter complex, allowing sustained bite pressure over extended periods without fatigue. This is the opposite of the Jaguar strategy. Where the Jaguar is a single explosive compression, the lion is a slow pneumatic press. It works, but it is slow. And in our TTI framework, slow means a lower rank. Here is where our data becomes uncomfortable. A leopard launching from a concealed position 10 feet away covers that distance in approximately 0.18 seconds. The arithmetic is simple. The strike lands 70 milliseconds before the human brain completes its first threat assessment. You lose before the visual signal reaches conscious processing. The motor response that might save you hasn't even been cued. This is not a matter of fitness, training, or awareness. This is a hardware limitation of primate neurology, measured against a system that has been under selection pressure for precisely this kind of engagement for 2 million years. Our team sometimes runs a thought exercise with new field researchers. We ask them to design from scratch the ideal prey animal for a large felid. The specifications always converge on the same profile: minimal integument thickness, no protective pelage, an exposed carotid artery positioned superficially in the anterior neck, bipedal locomotion limiting maximum sprint speed to roughly 27 kilometers per hour, and limited peripheral vision. Then we point out they have just described themselves. Humans present what we call evolutionary easy mode for these predators. Our skin averages 2 millimeters thick. A jaguar's canines are 50 millimeters long. We have no ruff, no mane, no dorsal ridge of guard hair to complicate a bite hold. Our carotid artery runs within a centimeter of the skin surface. We are, from a target-specific lethality standpoint, mechanically undefended. The only reason these encounters remain rare is behavioral. These cats generally avoid us, not because we are formidable, because we are unpredictable. And in the economy of predation, unpredictability introduces risk that outweighs caloric return. But remove that behavioral buffer. A surprise leopard, a habituated lion, a jaguar defending a kill, and the physics reasserts itself immediately. That is the data. The shadow moves faster than your ability to perceive it.